Moving into the Ash Grove with Lori Riley. Maggie Pickens. And by Kathy Mimin, this is the Black-Necked Swan. And ending with the Rainbow by Kathy Mimin. Do you need one more minute? Let's see, it's about 7:30. Is it 7:30? Oh, I have 5 more minutes. Okay. Okay. Oh, you know what? I could get, for the last 5 minutes, I'll get something super relaxing to listen to. And one is called Castle Kelly, followed by Parsons Farewell. There we go. I have 3 more minutes. This is Kathleen. And for the last minute, the fairies came in.
Kim, that was really wonderful. Thank you so
Thank you so
much,
much.
as usual.
Thank you for
It's always such a pleasure to hear that.
Oh, thank you so much. It's always a pleasure being here with you all.
And you'll be happy to know that the harp sounded really good in the auditorium here at
Oh, you were
Chapman.
able to hear it. Oh, fantastic. I
Yeah.
decided to move the camera a little closer to me and then Risa has me on original sound.
Great. Well, it seemed to be coming through great. So you got the right combination.
Awesome. Thank you so
Anyway,
much.
well, thank you. And I guess it's time to get started on the meeting. Um, everybody, welcome to the May meeting of Orange County Astronomers. We're delighted to have you. We have people that are filtering into the auditorium now. If you were here in person, you could take advantage of the coffee up there. I'm not sure about donuts tonight, but usually you have refreshments and other fun things and an opportunity to meet with your fellow club members. So, think about coming in person sometimes, though it is also great to see it remotely. Anyway, let me see. I guess maybe for those of you who don't recognize me, maybe I should introduce myself.
Oh, you got muted, Barbara.
Am I on now?
Yes. So we just heard you. You started to introduce yourself.
Okay, thank you, Reza. I'm Barbara Toy, and it's my privilege to start things off, and then I get to turn it over to other people who can handle it more competently than I would be able to. So I think it's time for our club announcements with Kyle. And ready to go, Kyle?
Yep. All right. Let me just pull up the slides. All right. Welcome, new members. You can find your name badges either on the whiteboard right behind Barbara, as you can see in her picture. And if you're not attending in person, your name badges will be mailed to you after a couple months. Our next ANSA Star Party will be June 8th. Astrophysics Special Interest Group will be meeting May 17th. Beginners class June 7th online, and the board meeting will be July 28th online. And Astrophysics is meeting at the Heritage Museum. You can find more information about all of our events online on the OCA website. The annual trip up to the Owens Valley Radio Observatory, hosted by Dr. Doug Millar, is coming up soon. If you're interested in that, please reach out to Doug Millar. His contact information is below. It's always a very fun trip. You can probably see a very young Kyle there in that picture on the bottom. Anyway, it's always a great trip. And all the activities are free of charge. You just have to cover your own food and accommodation. So it's a great low-cost way to experience a great science weekend. The next beginners class will be, the next How to Use Your Telescope beginners class will be July 5th at the Heritage Museum. This class is really helpful if you're new into astronomy and need some help learning how to use a telescope. This is a hands-on class where there will be people there to help you learn how to use your scope, and it's a great resource. The outreach event program is currently on hold. We're looking for a new outreach coordinator. If you are interested in help in being that coordinator, that would be someone who helps administer the program and helps get other volunteers for the outreach events. Please contact Alan Smallbone for more information. We are also looking for a social media coordinator. If you are willing to help with that, we'd love to get our Instagram, Facebook, and Twitter accounts more active. This is a volunteer role. There's a lot of flexibility in what this role can look like. If you're interested in helping out with that, please contact Reza. This is just a reminder about our Adopt Scope program is up and running on our website, as you see here. You can see the current inventory along with the sample adoption agreement, and there's more information there about how the Adopt Scope program works. The Serious Astronomer newsletter is always looking for new content to fill our monthly newsletter. If you have any items of interest, such as articles, images, trip reports, etc., please contact Dave Fisher, and he'll review those items. Reminder that everyone always receives a printed copy. However, if you'd like to opt out of receiving a mailed copy, please email Charlie, as all club members always have access to the newsletter in the electronic format on the club website. Again, everyone receives a printed copy unless you opt out. Reminder to help with keeping your pad and the observatory areas clear of weeds at the ANSA site along with the common areas. We appreciate your help. The next meeting will be, general meeting will be June 14th, and I will turn it over to Chris Butler for the What's Up presentation. Thank you.
Buddy, hi, this is Chris here, and we are preparing to launch the What's Up. Thank you for doing that after showing me earlier how to do it. And I freeze up, in front of large audiences. It's the panic of the thing. All right, good to see you all. Gosh, fantastic. Thank you so much. Top-notch service. This is what sets us apart from the Turtle Club people. It's the level of service that we have here. Thank you. This is the What's Up part of the program. We're going to talk about
Chris, if I may interrupt you,
please do.
Since you mentioned about the level of service, can I ask Sam to have a camera angle adjustment, please? Your head. Oh, yeah, there we go.
Raise the bridge, lower the river. Yeah, we do have a variety of different heights represented in the club. All right. Hold on. I can't do all of them at once. Hold on. We're getting it. We're working at a situation. They're rigging some block and tackle from the ceiling. So no, actually we're getting it. Just a moment. I have to keep remembering that not everybody in the club is seeing live from ANSA. All right, well, you remember, Charlie remembers, yeah, when we would do the live broadcast. Look at that. Well, I don't know. That's a little tall. Maybe we could, yeah, I can just like this. No, I'm messing with you. I'm sorry. All right. Are we? Yeah. All right. Yeah, here I am. So yeah, it's really me. I'm still doing the What's Up. So cool. Okay.
Okay, perfect. Thank you very much.
It's perfect. All right. Absolutely. Not every club would do this. So the model railroader people, they don't care about camera placement. Okay, we're all set. All right, fantastic. Let's launch into the What's Up and see if we can find out what's going on. Going to find my button. Okay, fantastic. As far as what's going on with the sun, it was a little strange coming to the hall tonight because, of course, it is still bright sunshine even at this hour. We are, of course, having longer and longer and longer days, shorter nights. We're coming up on the summer solstice, which is going to happen on June 20th. The longest day we can ever have at this latitude is 14 hours, 24 minutes. Tonight, we are at 13 hours, 49 minutes. So we're having very long days right now, coming up on the beginning of the summer season. Of course, it's always summer in California, as you know. Looking at the phases of the moon, I'm a big moon fan. What's going on with the moon? The moon has just passed through a new phase on May 7th. We're a couple days past that, so we have a thin crescent moon in the evening sky. And for the next week or so, the moon will be conveniently placed for observation in the evening sky, swinging around towards May 23rd when we're going to have a full moon. And then you'll notice we end at least in this diagram, we get through to June 6th. It's kind of interesting for last quarter. It so happens that the lunar cycle started so early in the month, just happened to, that in fact, we go through to another month at the end of that. The months and moons do not always line up. This is one of the times you get a little bit strange dates there. Don't worry, though. They are accurate. Looking at the planets, if we have any planet fans, Mercury is in, well, actually, it's kind of interesting with the planets in general right now. You may have been wondering, where are they? And the answer to that is that they're all online. They're all yeah, they're sitting there watching TV instead of being in the sky. We do have lots of plants, all the ones we used to have, but they're not well placed for looking at a convenient hour. Mercury is a good example of that. We can see it in the morning sky before dawn, or we can see it in the evening sky after sunset. It's over in the morning sky. It's not that bad right now, but you have to get up very early. Okay, it doesn't rise until 4:49 a.m. So Mercury is in the morning sky. So too is Venus, but just barely in the morning sky. It's only 6 degrees from the sun right now, so it is essentially invisible. You'll see a map in a minute. Mars is naked eye bright, its first magnitude. However, it doesn't rise till just almost 4 in the morning. So it too is a pre-dawn object. A side note for you, you'll notice the abbreviation of CET for what constellation it's in. And if you're searching your zodiac memories to find out which constellation that is, actually, does anybody know which constellation Mars would be in if it's in CET? Cetus, absolutely. So if you see Mars, point to it and say, Cetus. Just kidding, just kidding. Been saving that one for like years. But no, it does cross barely into a few other constellations. The zodiac planets do that, but not for very long during their orbits. But right now, Mars is in Cetus. Jupiter is just like Venus, but on the other side of the sun. Jupiter is in the evening sky, setting after the sun. It has been for a long time. You probably have been watching that in the evening skies, but right now it has gone so low in the evening skies. It's only 5 degrees from the sun and effectively invisible. It will drop further down, go completely behind the sun, and emerge in the morning sky. Saturn is actually a little bit more convenient. It's also a pre-dawn object, but it rises at the very early hour of 3 in the morning. So if you're up at 4 or 5 in the morning, yes, you can see Saturn, but I don't tend to get up that early myself. Uranus is in theme with everything else. It is not only near the sun, it's freaking behind the sun right now. I mean, just very nearly exactly. So it is completely having none of this planet visibility stuff going on. As far as Neptune again, a morning object rising at 3:32 in the morning. Pluto is having its moment where all these other so-called planets have decided to abandon their posts. Pluto actually rises at the much earlier hour of 1 a.m. at a more convenient time. So if you want to catch a planet, really, Pluto's just about all you can do. This shows the sky as it appears at about 8 p.m., not long after sunset. And I have cheated here to show you stars at all. The sky would still be far too light at this hour to actually see any of the stars or planets. The reason I mention it, you see the moon labeled on there as a crescent. It doesn't really look like that. This is a map. You see where the moon would be. But if you look down in the sunset, you can see Jupiter almost behind the sun now. So that's giving you an idea why you really can't see it at this time. If you give it another hour, 9 o'clock is about when true darkness sets in at this time of year. And again, you can see the moon, but you can't see Jupiter. It's already gone. The constellations we're looking at this hour, if you looked into the west, which is on your diagram to your right here, you would see the wintertime constellations setting, the Gemini, the twins with Castor and Pollux. Orion is finally up to his hip in Pacific Ocean and settling lower by the minute. Winter is most assuredly over. It's the springtime stars that are stealing the show now. Constellations like Ursa Major, just about center on this diagram, meaning straight up. Ursa Major, the Great Bear, home to the star pattern of the Big Dipper, of course, beautifully placed in the early evening hours. We also have Leo the Lion. Leo is beautifully placed as well. But rising up behind it are some other constellations, which will focus on actually the area right around straight up. And let me zoom in there a little bit there. You can see Ursa Major at the top, which is towards the north, Leo, which should be towards the west. And then you see toward the east, the bright star Arcturus marks Bootes. Bootes, the bear driver, chasing as the Earth rotates. The logical purpose is to keep the bear away from, I guess, his farm and crops and so forth. Probably there should be a garbage can constellation if this is a bear. I never really thought about that before. And then down in the south, we also have a constellation, the southeast, which is Virgo, the harvest maiden, marked by the bright star Spica. So those are the traditional bright constellations of the spring, which are just about straight overhead. I am going to focus at least a little bit on Bootes because it's shaped like an Imperial Star Destroyer, and this is May not the 4th, but May the 4th was recently here. But also because it's one of my favorite constellations. And we'll talk about that a little bit. But I want to draw your particular attention to, in the center of all of those springtime constellations, we have two fainter constellations, Coma Berenices and Canis Venatici. Both of those are ones that have a lot of objects to look at. And maybe some of you, if you're relatively new to amateur astronomy, you haven't checked those out yet. So I want to direct you that way. Here's a very official looking chart from the International Astronomical Union of Bootes, and you can see it forms the shape of basically a big ice cream cone or Imperial Star Destroyer with the bright star Arcturus drawn by the large black dot at its southern tip. Arcturus is a noteworthy star, and I will call attention to some of its qualities there. It's the 4th brightest of all the nighttime stars. Right behind it are Vega in the summer sky and Capella in the winter sky. But Arcturus is the 4th brightest, and it is the brightest star north of the celestial equator. So the only brighter stars are in the southern half of the sky. That doesn't mean we can't see them. Sirius is number 1. Canopus is number 2. We can barely see Canopus on our southern horizon. And then there is Alpha Centauri coming in at number 3. Well, next one is number 4, which is Arcturus. You can see some of its qualities. It is a spectacularly powerful star, 170 times brighter than our sun. It's 25 odd times larger than our sun. It, however, notably is about the same mass as our sun. I mentioned that for fans who have been reading about the eventual fate of the sun. I mean, well, after this current solar outburst we're all going through, but several billion years from now, the sun will do the red giant trick. And if you ever wonder what that would be like, this star, Arcturus, is the same mass as our sun. It is doing the red giant thing right now. It used to be a star very much like our own. The reason it's going through this right now is it's much older than our sun. We're about 4.6 billion years old, and it is about 7.1 billion years old. So you are, in a way, seeing our future by looking at the bright star Arcturus. One interesting note, you're also seeing our past, because this star is 36.7 light years away, not too far in the galaxy. It's a reasonably near neighbor. That means it took that long for the light to get here, which means, of course, you are seeing that star 36.7 years in the past. That's how long it took the light to get here. And if you go back that far in time, when that light we're seeing tonight left the star, this is what the lecture hall here looked like. And I believe, in the shot down in the front row on the bottom of the left there, I think I can see my dad in the audience. I can see, oh God, Charlie's still treasurer. Of course he's treasurer. A lot of the same usual suspects. And there we all are sitting 36.7 whatever years ago, Arcturus time in the distant past. That's kind of a fun thing to think about. One thing I did, by the way, when I was doing research a little bit on Arcturus for you all, and it's a resource I want to let you know about. This is a website of the U.S. Navy. You may not know, but the U.S. Naval Observatory is a critical office of the U.S. Navy because they were involved with celestial navigation. Celestial navigation for ships drove development of astronomy in many different ways around the world. So USNO back east publishes the most authenticated, verified conditions in astronomy, things like this inquiry, which I launched to their website. You can, asking when Arcturus's rising, transit, and setting times were. So this is an official Navy document telling me that on that day from Anaheim, California, exactly when that star would do these things. That's critical for sailors to know, of course, if they're measuring the star's height to figure out their location on Earth. One other related note, all of these ships are named USS Arcturus. It turns out that our Navy and many other navies around the world, because of the importance of celestial navigation, have a tradition of naming ships after stars. And so we've been doing that for a long time. And Arcturus is one of the most important navigation stars for sailors because of its brightness, and it's relatively isolated in the sky. It's not in a crowd of other bright stars that you might mistake it for. So you finding Arcturus, you're stepping in the shoes of many famous and important navigators throughout history. Now, right next door to the constellation of Bootes, just slightly to the west, is Coma Berenices. And of course, you will all know that means the hair of Bernice. Which it does actually mean the hair of Bernice. Theoretically, this constellation was created after some of the priests in, I believe it was Ptolemaic Egypt. The queen Berenice had cut off her hair and laid it on an altar as a gift to the gods. And in the morning, the hair wasn't there. Apparently, somebody had like a hair thing. Okay, and they took the queen's hair. And I don't know, whatever. But the thing was, the priests saved the day in the morning by saying, "Oh no, it wasn't stolen. It was lifted up into the sky, and those very faint collection of stars you see next to Bootes, this little sparkling, misty part of the sky there, that is the queen's hair." So Coma Berenices, that's the rumored tradition of how it got its name. And the stars in the constellation are actually a star cluster, the Coma Berenices star cluster, which is basically the whole westward part or rightward part of that constellation. There is a large gathering of faint naked eye stars. You can see them, but not brightly. It does look a little bit like a large hazy spot to your eye. So that's where they came from. This is the constellation that is almost directly straight up out of our galaxy, up and down our arbitrary. Galactic north is the direction. The main thing is that's a great place to look for other galaxies in the distance without our Milky Way blocking the view. There are many, many, many famous galaxies here. You'll see pictures of a couple in a moment. But before we do that, here is a picture of that scattering of bright stars, the Coma Berenices star cluster, a group of stars about, I think it's in the ballpark of 200, 250 light years away, something like that. I have to double check myself on that. But it's not that close by, but it is large enough close enough that it's large in the sky. So it's a big scattering of stars. A pair of binoculars will show it to you just fine. This picture, if you are being scrutinizing and very picky, you in the audience will notice it is a grainy picture, and yet I included it. Have our standards slipped? No, there is a reason, because this picture is interesting and unique. This picture was not shot on Earth. This picture was shot from the International Space Station by astronaut Don Pettit. So we are now living in an era unlike those 40 years ago when I can show you astrophotography taken from other places in the universe. So that's a very pretty picture of that star cluster. Here's something that is a big telescope, picture of galaxy M64 in Coma Berenices, famous as the Black Eye Galaxy. He would clearly walk a mile for a camel. And this is a galaxy, a big spiral galaxy with a lot of dust, particularly on one side. Theory is that it probably collided with and ingested another galaxy, and that's why we have this unusual formation of dust in it. It can be seen in amateur telescopes as well. Here is a picture shot by our very own Bill Hall. Bill Hall is a noted astrophotographer in the organization, and this is from the OCA's image collection, which is on our website. I invite you to look at it. This is a beautiful spiral galaxy, which is seen edge on, the Needle Galaxy, or NGC 4565, also in Coma Berenices. This is kind of a ghostly view. It won't make you fall off your couch in terror and clutch your chest. This is what things look like through telescopes. This is actually not a photograph at all. It's a drawing. And a drawing or a sketch through the eyepiece can give some of the most honest impressions about what things really look like when you put an amateur telescope, in this case an 8-inch telescope, on an object. And this happens to be my favorite kind of object, a globular star cluster, in particular M53 in Coma Berenices. Now, the challenge, of course, is that although it's beautiful to see this little sparkling of stars and so forth, you know what people want these days. People want this, right? And of course, space probes and giant telescopes, and they can take these kinds of pictures. This is what it really is. It's an honest photograph of this object. Just do bear in mind that if you buy a new telescope for Christmas and you've seen that, and you end up with the preceding view, don't complain. It's perfectly fine. All right, there we go. The Coma Berenices galaxy cluster is distinct and different from the Coma Berenices star cluster of stars in our own galaxy. There is also a cluster of galaxies in the background, way in the background, about 350 million light years away. You've heard of the Virgo cluster of galaxies, probably. This is quite a bit farther away into the background, behind it, but almost in the same direction. And that makes the galaxies a bit smaller and a bit fainter. But there are a lot of them, and for experienced observers, diving around the Coma cluster of galaxies can occupy many a happy hour. Right to the north, in fact, passing straight overhead in the evenings at about 10 o'clock tonight, is Canis venatici, the hunting dogs, with 2 stars, Cor Caroli, and the unlabeled and yet fully worthy Beta Canis venaticorum that has the name Chara. Those 2 stars mark the 2 hunting dogs, okay? This constellation is also riddled with lots of galaxies that you can have a look at, but I am going to first talk about Cor Caroli. The name may have surprised you. You may wonder what in the world gives a star a name like Cor Caroli. The name actually means Heart of Charles, Cor, Cœur in your French there. Cor Caroli, why was it named for King Charles? Well, of course, first of all, the question would be, which King Charles? Because there are plenty of them as you keep them going. There was one of them that got this star named after them. And what did this particular king have to do to get a star named after him? And the answer, of course, is get his head cut off. Which would be Chuck the First, all the way on screen left. Charles the First, when he was beheaded, some loyal servant of the king said that that particular star shone with unusual brightness. It got the nickname Cor Caroli, and that has stuck. But this is really a tragedy, not only because of the people who died in the English Civil War and all that, but also because all Chuck had to do was send in $50 to the International Star Registry, and he could have gotten the star named after him without getting his head cut off. So I'm just trying to save you all a lot of trouble and needless decapitations. There are of course, these star naming things are not official, as you understand. To get a star really named after you, you do have to get your head cut off, but that's another thing. I'm kidding, by the way. We got to remember the lawyers for the club are watching this. Globular cluster M3 is in Canis Venatici, and it is one of the most beautiful of the globular star clusters. It's closer to us than M53, so it appears larger and brighter in our telescopes. So I strongly, strongly recommend you have a look at this. This object is so famous, probably people in the room are wearing it on t-shirts, it's on keychains, M51, the Whirlpool Galaxy. This picture also shot by an OCA member, Arnie Rosner, from a number of years back, shot this beautiful picture of the spiral galaxy locked in a gravitational dance with its companion galaxy. M63 is another one of my favorites, a beautiful, delicate sort of spiral galaxy in Canis Venatici. And then we have this highly dynamic picture of galaxy M106, almost up in the border with Ursa Major in the north of Canis Venatici. And there are oodles and oodles of others. Bill Hall, another picture from him here of the very, very active nucleus galaxy M94. Pictures don't do this credit, really. This is one where there's a major party going on in the core of this galaxy. It's really bright. So you have kind of this soft, round, ghostly glow, and then this fuzzy, really bright thing in the center there. It's shown in the picture, but you really have to put your eyes on it to understand the power of an active galactic nucleus, M94 in Canis Venatici. Let's go back to the stars real quick to wrap things up. Midnight. Notice we have let the stars rotate around, but if you look for the areas we were just looking at around Ursa Major, Boötes, and all, you can see Coma Berenices and Canis Venatici, and they're still very high in the sky. That's a benefit of a constellation that's relatively north in our skies, like this, that are very, very high above the horizon. They tend to stay up a long time. So the whole evening could go by, and these objects would be available for you. But still no planets, notice? Well, all right, get out your coffee. 4 a.m. You've been waiting for it, and finally they showed up. The Milky Way is out, the summer Milky Way, and you see a whole parade of planets appearing there. Pluto is, of course, first among them if you're hunting with a big telescope. But there's Saturn, visible to the unaided eye in Aquarius. Neptune, you need a telescope for, of course, is not too far away. And then Mars, naked eye, bright, but not very high, even at 4 in the morning. And then as the dawn begins to break, you see where all the other ones were hiding. You can see Mercury and Venus. Venus essentially invisible at this time of year. So there's plenty for you to hunt all the galaxies that we talked about. And then the planets will eventually get into a little bit more convenient positions later. With that being said, we do have summer coming in California. That means getting out there and being with people, going to the beach and cookouts and family gathering. I'm just kidding, of course. We're astronomers. What I mean to say, it's times for being alone in the dark with cold, hard pieces of technology we spent tens of thousands of dollars for because we don't want to be with people. I'm just kidding. But beautiful stars going to be available to us all summer long, and I look forward to that. And in the meantime, have fun with the galaxies. Thank you very much.
Thank you very much, Chris, for yet another wonderful presentation. And I particularly liked the blast from the past. That was great. Thank you very much for including that. So without any further ado, let me go into introducing our speaker at this meeting, who's a mineralogist and planetary scientist with expertise in crystallography and the application of data-driven techniques. She's the co-director of Carnegie's 4D Initiative and co-investigator of the Chi-Mean X-ray diffraction instrument on NASA's Mars Science Laboratory mission. She's moving to Rutgers University in the Department of Earth and Planetary Sciences as an associate professor in September 2024. Please join me in welcoming Dr. Shaunna Morrison. Shaunna.
Thank you so much for that introduction. And I will go ahead and share my screen. I am really thrilled to be here virtually with you all. I wish I could be there with you all in person. It sounds like I would really love to be there for some of your club events, which just sound so cool and fantastic. So next time I'm in LA, I might try and tag along with one of your trips. Can you see my screen okay?
Yes, all good.
Okay, fantastic. Great. So thank you again so much for having me here. I'm really thrilled to be here with you all today. And I'm very excited to have the opportunity to share with you some brief highlights of my exploration of data-driven discovery and evolving Earth and planetary systems via mineral informatics. I'd like to start out by telling you how I started out, or at least how and why I started moving my science towards this more predictive space. So I'm a mineralogist and a crystallographer, and historically in mineralogy and in my classical training, we measure and describe materials that we find in nature or we create in our laboratories. But with this careful compilation and curation of large data resources and the utilization of advanced mathematical and visualization techniques, I've had the privilege to be a witness and to be a part of moving mineralogy from a very descriptive space into a much more predictive one. And we've been able to do things like predict the number of missing mineral species as yet to be discovered on Earth's surface, predict the location of previously unknown mineral deposits, characterize planetary scale biosignatures and the diversity and distribution of mineral species across a planet, and predict the previously unknown formational environment of a mineral sample, including whether or not there was biogenic input into that formation. I think that's pretty exciting and pretty cool, but it's really just the tip of the iceberg. And this has led me to my vision for the future of Earth and planetary science, and it is that it is data-driven, employing powerful predictive machine learning methods to exploit our large and growing data resources. And it is integrated across many different disciplines, many fields of science, and it also embraces the complex multidimensionality of our natural systems. So this way of thinking enables me to ask questions like, how have planets evolved through deep time, and what are their drivers of their similarities or their differences? I think you mentioned earlier, you said, oh, for people who like planets, well, I love planets. We're going to talk a lot about planets, including Earth, but other ones in our solar system. I also want to know how we can deconvolve and characterize the complex feedback systems between Earth's geosphere and its biosphere. And what are the mineralogical signs of life, and how can we detect them on other planets? You might wonder, why are minerals the best tools to unravel the mysteries of our solar system, to better understand the history of our planet, or to learn more about the origin and evolution of life on Earth, or perhaps elsewhere in the universe? There are many reasons to study minerals, not only just because they're cool, but they are very cool. There are a lot of really cool mineral clubs out there too. If you're looking for another club to join, those are pretty cool active clubs. But aside from their coolness, some of the key reasons are because minerals are the oldest and most robust materials in our solar system, and therefore the only physical evidence of our most ancient geologic and biologic past. They're the only things that we can hold in our hand from those time periods, the only things we can examine in our labs. And also, because minerals and life co-evolved, they were each influencing the other. Life emerged and evolved in direct interaction with minerals, and likewise, minerals and the geochemical landscape evolved in concert with that biological activity. And fortunately for us, minerals are time capsules, retaining information about their formational conditions and any subsequent weathering and alteration they've undergone, including whether or not there's biological input into that formation. So minerals have the story of Earth, the story of our solar system, all locked inside of their complex data attributes. And it's up to us to decipher what they're trying to tell us. And for me, that's where data science comes in. So you might be wondering, why do I think data science is so important to this? Why is it the best means to study these natural systems with a mineralogical lens? Well, again, many reasons. But firstly, and what initially drew me to data science is the fact that it is multidimensional and multivariate. It allows us to embrace the complex multidimensionality of these incredibly information-rich mineral systems. And you'll see as I go through this talk, I'm only really just touching on just a small amount of the information that is contained within minerals, and it will still give you a great picture of, wow, there's a lot that we need to integrate here. Speaking of integration, I also quickly became appreciative of its integrative power. So mineral systems do not exist in isolation. They are intrinsically connected to the surrounding geochemistry, geobiology, normal biology, not related to geobiology, physics, astronomy, and so on. And they are a part of these very complex systems, and data science is the common language between fields. So it gives us this interdisciplinary system scale holistic view of natural systems. Now, I recognize that I am speaking to an astronomy club, so I want to just step back a little bit, and I keep using this term mineral, and some of you may be familiar with it, but in case some of you aren't, I'd like to just define what I mean when I say that word. And to be fair, mineralogists don't always agree on what we mean when we say this word, so I'm going to tell you what I mean when I say it. A mineral is a naturally occurring solid that has both a well-defined chemical composition, like the olivine group N member forsterite, which you can see here on the left. It's Mg2 SiO4, and also a well-defined crystal structure with the structure of forsterite shown here on the right. Now, before we dive into the projects, I'd like to just briefly mention a couple of data resources we're using. I'm not going to cover them all, so please feel free to reach out if you're interested in a data set that I've not shown you how to get to here. I'm going to hit the really big ones that I think might be of interest to you. And note that all of these resources are publicly available, so please feel free to explore them and use them for your own work. So to start, we have the International Mineralogical Association's list of approved mineral species, which is hosted and run by the RUF Project at the University of Arizona. Bob Downs happens to be my PhD advisor. There are 6,006 distinct minerals recognized by the IMA as of this morning. I checked just for you guys. And so on this website, you can search for a particular mineral. You can use a chemistry filter. You can also search on the many tags you see there on the right. And you can also click this link here to reach the Mineral Evolution database, which is a very cool database that was pioneered by Bob Hazen, who I work with at Carnegie, and it represents countless hours of literature review. Josh Golden from the University of Arizona has led the data collection, and he did much of it himself, but also trained a lot of undergraduate student workers. So basically, this database contains location information for minerals on Earth's surface, many of which have an age associated with them, and it is huge. Currently, we have approximately 1 million mineral locality pairs and more than 160,000 mineral locality age triples. So it is a huge resource. Another great database is mindat.org. This website provides a list of minerals that have been observed at specific localities on Earth's surface, and a lot of images and a lot of other really cool information. And to date, they have more than 400,000 geologic localities characterized and more than 1.5 million mineral locality pairs. So it is huge. And lastly, I'll just mention EarthChem, which contains a huge wealth of geochemical information from rocks and minerals around the world and from extraterrestrial materials. In fact, this is the largest database for geochemical information in existence. So we use it a lot, and I recommend you check it out if you want to see some geochemistry. Okay, so now you know what motivates me. Now you know the kinds of questions I like to ask and some of the data that I'm using to ask them. So let's actually get into the fun part, the science. I'd like to run through some of these data-driven projects and discoveries that utilize mineral informatics. I'll mostly summarize some of them and the key findings. And then in a few of them, I'll go into more detail on some of the ones that are a little bit more recent. We'll give you a little bit more detail. So first, I'd like to mention a foundational concept that is a sort of a framework, if you will, and that is mineral evolution. So this concept recognizes the fact that a planet's mineralizing environments and therefore the resulting mineralogy are different at different stages of planetary evolution. And this offers a mineralogical framework for characterizing the physical, chemical, and biological conditions that planets have undergone through deep time. So what do I mean by this? Essentially, the minerals that were forming on Earth 3 billion years ago are quite different from the minerals that are forming today. Likewise, the minerals that form in a biologically driven environment are going to be very different than those in an abiotic environment. So let's look at the evolution of Earth's mineralogy. We start well before Earth. We start with pre-terrestrial and nebular environments. And in those environments, we can form 109 distinct mineral species. Next, we have planetesimal differentiation and alteration, which can produce 261 distinct mineral species. Then we start forming the earliest crusts on Earth. That was during the Hadean. On Mars, we call that the pre-Noachian period or era. And with these environments, we can form up to 400 distinct mineral species. We then have the earliest hydrosphere, and those processes result in 350 mineral species. Now, this is really where Mars likely stopped in its bulk mineral evolution. We've continued to have aeolian activity, but aside from these processes, we're not really aware of any major drivers of mineralization. What we don't know is if it had an anoxic biosphere. And there were likely some other surface processes that could have taken place on Mars that have occurred on Earth, but largely Mars bulk mineral evolution stopped with the earliest crusts and earliest hydrosphere. And that essentially means that there are around 1,100 mineral species that are most likely to exist on Mars. Earth, of course, continued on the path of planetary and mineral evolution, forming continental crusts, having high temperature alteration and metamorphism, a range of surface processes, and of course, the initiation of plate tectonics. Igneous rocks continue to evolve, and we got unique, highly evolved rocks. We obviously had an anoxic biosphere. It's unclear exactly when that originated or whether or not it also exists on Mars, but there are 11 distinct mineral species that are associated with that. Now we're up to, this is like 2,000 mineral species-ish, 2,000, 3,000. But I told you that there are 6,000 mineral species, right? So what was the driver of this doubling of mineral species, right? This is in part biologically driven. Okay, and this is part of what I like to think about and study. So we have the Great Oxidation Event. So that brought about over 2,300 of the 6,000 known mineral species on Earth today. And these processes continue to form minerals, but for some time during the intermediate ocean and snowball Earth periods, we really don't see any new mineral speciation, not until we get into the Neoproterozoic oxidation and the rise of the terrestrial biosphere. Right, so life is playing this huge role, and we're seeing a boom of almost 600 mineral species during that period into the Anthropocene, which of course is where we see another diversification event, and we play a big role in that. Okay, so what have we learned with this way of thinking or within this framework of mineral evolution? We've learned a lot, but I'll just highlight a few of those findings. We found that there are pulses of mineralization associated with supercontinent assembly. We found that Earth's atmospheric oxidation is recorded in its mineralogical record, and you can very closely track it, even how long it takes for the subsurface to be oxidized. And there's a strong increase in mineralization with the rise of the terrestrial biosphere related to things like skeletal biomineralization and root systems and clays. So the next project I'd like to mention is mineral ecology. With these studies, we found that Earth's mineralogy follows a very distinct distribution. It's called an LNRE, or large number of rare events trend. It's kind of related to Zipf's law, if you're familiar with that. But basically what it means is that most mineral species are rare. They occur at 5 or fewer localities. Most occur at only 1 or 2. And there are only a few very common species like quartz and calcite and the feldspars. So we can model this trend and make accumulation curves similar to those used in ecology to predict the number of as yet undiscovered mineral species on Earth. So here you can see the frequency distribution of vanadium minerals. This distribution and its resulting accumulation curves allows us to predict the number of missing mineral species for vanadium, which was 88. Since this paper came out, 64 of those 88 minerals have been discovered. And overall, we predict there are around 9,000 total mineral species, at least, likely in existence on Earth right now, but we only know of 6,000. So there are 3,000 species left to be discovered. So if you want to discover new minerals, lots of opportunities. One of those opportunities was the Carbon Mineral Challenge. This was a part of the Deep Carbon Observatory. And over I think it was a 3-year period where this was active, it led to the discovery of 40 of the missing carbon mineral species. So if you're interested, please check out mineralchallenge.net for more information on that study and the minerals that were discovered. I was actually involved in one of those, a rare earth element mineral, which is pretty cool. Okay, so my next question is one in the next project I'm going to shift to. The question here has really plagued geologists, collectors, all sorts of people for hundreds of years. And that is, where can we find previously unknown locations of minerals or mineral deposits? Likewise, where can we find mineral assemblages that signal a geologic process or an environment that we're interested in to go study or explore? Association analysis is a recommender system that characterizes multidimensional co-occurrence relationships and creates a probabilistic model for future or currently unknown co-occurrences. So what does that mean? Most of you actually are very familiar with these types of algorithms. You encounter them all the time with companies like Amazon or Netflix when they make recommendations to you about what you might want to buy or what you might want to watch. And like Amazon or Netflix, we can apply this to mineral systems because we also have a huge database of mineral co-occurrence on Earth's surface. So we can look at these multi-mineral correlations and give probabilities of where else we expect to find a given mineral, a mineral assemblage, or a geologic environment on Earth or another planetary body. So it enables us to ask questions like, where can I find a new location of a mineral I'm interested in? This could be something like a deposit of strategic minerals, or if you're a collector and you're looking for a certain species and you want to go find them, so you want to find all the places on Earth, we can help you do that. We can also use mineral assemblage to predict the location of a previously unknown planetary analog site that we want to go study. And we can also produce a mineral inventory at a particular site of interest. And I just want to make it really, really clear. We're not simply looking for places that are known to host the mineral assemblage in question. We can do that easily by just querying MinDat or the Mineral Evolution Database. What we are looking at is sites that are not known to host all of the mineral phases, but have a high likelihood of hosting them. And it's just that no one has reported them there yet. So we're looking at complex correlations and anti-correlations of mineral occurrence to make predictions about the probability of that location being an analog site. Okay, so how do we do this? I'm not going to get into the math of it, but we do this by generating a list of association rules, and this is what they look like. It's actually quite straightforward how you interpret this. So for example, if you have calcite, pyrite, quartz, and sphalerite at a particular locality, you have a certain likelihood that that locality will also contain chalcopyrite. And there are various metrics for quantifying that likelihood, including support, confidence, and lift, which we evaluate in conjunction with one another depending upon the type of question that we're asking. So we've used this method to conduct several case studies, and one of which we examined Tacoma Basin, which is, I don't know how far that is from you guys, probably not very far. And this is a Mars analog site of sorts, and it was used for testing some of the instruments on board the Mars 2020 Perseverance rover prior to launch. And at this locality, we knew what minerals had been observed previously, and we wanted to predict what other minerals we would expect to find there. So we were able to predict several phases, including some we might expect to find in a Martian environment, like hematite, pyrite, gypsum, magnetite, and so on. So we're able to update that likely mineral inventory of Tacoma Basin and possibly similar sites on Mars. These predictions have not been ground truthed yet. So if one of you guys want to go out there, it's not that far, right between you and Vegas. So you could go out there and check for me. But in another case study, we've examined critical minerals in the United States, specifically monazite CE, which is a source of rare earth elements, and spodumene, which is, of course, a source of lithium. These are critical elements that are essential to the development and proliferation of green technology. So we predicted several new localities in the US for each of the phases, and you can see them there. The localities are things like Jensen Quarry in California, and I don't know how far that is from you, but maybe not too far, and Litchfield County in Connecticut, which is a little farther. But we were able to do something really neat with these predictions. We'd made these predictions about a year prior to publishing the paper. So right before publication, I was looking at this list of predicted occurrences, and I wondered, has anyone found these minerals at these localities since we made these predictions a year ago? And sure enough, many had. If you look at the ground truth column, you'll see that several of these minerals were found at these localities after we made the prediction that they should be there, which is pretty cool because it's not often in science that we have our theories and our predictions so quickly ground truthed and proven to be correct. So it's extremely exciting. And I hope as you're looking at this work, you're thinking about how much more we can do with this, or maybe even what you could do with this. And there is a lot. There is a lot that can be done. This approach offers nearly endless opportunities in Earth and planetary science alone, and the opportunities outside of that are massive. So some of the ways in which we're expanding what we're thinking about specifically are to incorporate more context, including geologic setting, rock type, tectonic setting, geochemistry, age, vegetation. Actually, it can tell you a lot about the underlying mineralogy, microbial populations, getting into those geobio questions. We're also working to optimize the algorithm to perform on regular computers, or at least stop crashing supercomputers, because we tend to do that a lot. So we need to do some optimization of these methods. And through this optimization, we will also be able to do things like include rarer species, so minerals that occur at 5 or fewer localities. We'll be able to examine larger data sets. We'll be able to incorporate absence in addition to presence, because absence of a mineral can tell you something as well. And we'll be able to expand our prediction to other planets. I think a lot about Mars, of course, but we could do this elsewhere as well. And this work opens us up to so many future opportunities. Just some of the ones I'm thinking about are those of space exploration, in which we can target certain bodies or landing sites due to their mineralogical makeup or the environment that created their mineralogical makeup, right? We're also actively working on projects to better characterize the coevolution of the geosphere and biosphere, specifically thinking about trends in mineralization associated with microbial populations and functions. And we're also looking to expand this beyond mineralogical predictions, so to make predictions in soil, fossil, microbial, and molecular systems, which I think is pretty cool. My colleague, Anirudh Prabhu, who is the data scientist who works with me on this and is really responsible for developing these methods and making these innovations, he is actually working in some astronomy projects. So if you want to learn more about what he's doing, just feel free to reach out to me and I can connect you, because what he's doing is pretty cool, and some like exoplanet characterization stuff. So like I said, the possibilities with this method are nearly endless and very exciting. Okay. Next project. So now we're going to transition to this new project and another planet. So let's move over to Mars. And the next big question I really want to talk about is, can we predict complex mineral compositions on Mars? So I work on the NASA Mars Science Laboratory Curiosity rover mission, and our primary scientific goal is to explore and quantitatively assess Gale Crater as a potential habitat for life, past or present, and to characterize the geologic history of this area. Curiosity has 10 instruments, including ChemIn, here inside the body of the rover. And ChemIn stands for Chemistry and Mineralogy, and it's an X-ray diffraction instrument that definitively detects and analyzes minerals. We refine the X-ray diffraction pattern, or XRD pattern, to identify which phases are present and to determine their abundance and unit cell parameters, which gives us information about the structure of a mineral. More on that in a second. So as I mentioned earlier, minerals record the geologic and biologic history of a planet. So it's critical to understand the structure and composition of the minerals present in Gale Crater. However, while ChemIn can identify the mineral phase and its structure or its unit cell parameters, there are no spacecraft instrumentation capable of measuring the composition of a single mineral phase directly. There are instruments that can measure bulk rock composition, but nothing that can tell us the composition of the olivine or the pyroxene or the feldspar. However, fundamental crystal chemical relationships between X-ray diffraction data, specifically the unit cell parameters, and composition allow us to estimate the chemistry of individual phases with XRD data alone. And let me say a little bit about why we can do that. I won't go too far into the math of it, but if you recall my slide earlier describing what a mineral is, you'll remember that I showed you the composition, Mg2SiO4 of forsterite, which is that magnesium N number of olivine, and its crystal structure. Let's take a closer look at that forsterite crystal structure. And here, the green atoms are magnesium, the blue are silicon, and the red are oxygen. A mineral's crystal structure is defined by its unit cell, which is that gray box that you're seeing, and it's the crystallographic unit that's repeated over and over again in space to form this regular repeating crystal structure, or translational periodicity, if you will. That's the term we use. So this unit cell is defined by its dimensions, the lengths of the edges, length, width, height, ABC, and the angles between those edges, alpha, beta, gamma. Which are all 90 degrees in the case of olivine, nice and neat. They're not all like that. So we have magnesium in all of the metal sites in this crystal structure. But what happens if I add another element, if I substitute those magnesium atoms for something like, say, iron? The entire structure becomes larger because iron is quite a bit bigger than magnesium. So you see that the structure is becoming larger. And it turns out that as you add more and more iron to olivine, the crystal structure changes in a very regular and systematic way. So by mining a lot of experimental data from laboratory measurements, I can statistically characterize the relationships between the unit cell dimensions and the amount of iron. What this means is that when I get X-ray diffraction data from Chemin, I can accurately predict the amount of iron and magnesium that is present in olivine on Mars. There's no other instrument that can do that. And what's really nice about this technique is that we can do this for all the major minerals found in Gale Crater, not just olivine. So in my early crystal chemical work, relying on this relationship between atom size or ionic radii and its effect on the crystal structure, specifically the unit cell parameters, I was able to estimate major element composition of all rock-forming minerals detected by Chemin. So these were feldspar, pyroxene, magnetite, jarosite, and olivine. In this table, you can see an example of what those results look like for olivine, but it's important to note that in this work, due to the complexity of higher dimensional relationships, we had to limit the number of compositional elements that we could predict. In the case of olivine, we assumed magnesium, iron, only olivine. Now, this is a decent assumption. This is actually quite reasonable. But other components like manganese and calcium are present in minor amounts. And even though it's a relatively small amount, it actually can tell us a lot about the temperature, pressure, and other conditions of formation. So that's what we want to know, right? It's really important to understand these things and able to characterize the geologic history of Gale craters. This is exactly what we want to get at. But how can we do that? It's mathematically complex. So of course, I turn to machine learning, specifically labeled distribution learning, which is a method that can handle and fully characterize multidimensional unit cell parameter and crystal chemical relationships. Essentially, with this technique, we can predict major and minor chemical components in minerals with X-ray diffraction data alone. This method has the accuracy near that of a microprobe, which is extremely exciting because there's currently no spacecraft technology that can do this, and there will not be for quite some time. For those of you who don't know what a microprobe is, it takes up like an entire room, and it's extremely sensitive. We're not putting that on a spacecraft anytime soon. Okay, so how does this work? This method was actually developed for computer vision applications. They wanted not just to be able to say, this is an image of a sunset, or this image has clouds, water, sky, and buildings. What they really wanted to be able to say was how much of this image is clouds, how much of this image is sky, how much is water, buildings, and so on. So in other words, to describe the overall composition of this image. Well, that sounds a lot like what we want to do, but instead of describing the composition of an image, we want to describe the composition of a mineral. Of course, our input data look a little bit different. Instead of beautiful pictures of sunsets, this is what we have, mineral data. The minerals themselves are beautiful. Maybe the table isn't quite as beautiful as the sunset, but that's okay. So here we're looking at two instances of olivine phases, and we have the measured chemistry, which is those are our labels that we want to classify. And each value of a label is considered its degree. So the distribution of those label degrees across the instance is what we aim to classify such that we can make predictions of these labels for new future samples. And this is why we call this method label distribution learning. So the input data, which of course are the only data that we would have for a new sample we want to predict on, is then the structural unit cell parameters. So you can see there on the right. The LDL method is actually a framework that employs several different algorithms, things like, Bayesian techniques, support vector machines, all sorts of neural networks. We ended up trying all of these, of course, but the algorithm adaptation methods worked best for us, specifically k-nearest neighbor, which is interesting because it's one of the simpler methods, which was nice. And part of why that works is because the nature of our data in general, but also because our data is rather small in size. So KNN, k-nearest neighbor, outperformed all of the other methods. So that's what we're going with right now. And KNN is actually pretty straightforward and intuitive as a method. Just in case you're not familiar with it, basically the way it works is each instance of unit cell parameters is treated as a vector. The sample we want to predict the composition of also has a vector of unit cell parameters. And then in that vector space, we identify known samples in our model that are closest to or what we would call the nearest neighbors to the new sample. From there, we can take the average of the nearest neighbors weighted according to their proximity and calculate the predicted mineral composition. And you can set K to be as many samples as you'd like. 3, 5, 10 are common. 3 worked really well for our data set. So like I said, it's actually kind of straightforward. So not all machine learning is black box and everything like that, right? So here is what an output looks like when we compare it to the measured composition of that sample. We can see that this instance or this sample of olivine is mostly magnesium with a little bit of nickel. Those are what our results look like. So before, remember, I told you that in olivine, we could only do magnesium and iron. In feldspar, we were only doing sodium and calcium. In clinopyroxene and orthopyroxene, we were only doing 3 components: calcium, magnesium, and iron. But here we are now covering a huge chemical space with each of these systems. So for olivine, we're covering 8 distinct compositional elements, which you can see is rather complex compositional space. So here we're showing principal component 1 and 2, which account for about 75% of the variance in the PCA space. It's clear that the major elements, iron and magnesium, are dominating the compositional space, but it looks like manganese and nickel are also quite prominent in the olivine data set. In addition to those shown here, cobalt, calcium, zinc, and aluminum are also present in the data set, and therefore we can detect and predict their presence in samples on Mars. So if we look at feldspar, we're mapping even more elements, but they are generally minor components aside from sodium, calcium, aluminum, and potassium, which are shown in the PCA plot to account for nearly 90% of the variance. So mostly anything else is going to be present in minor amounts. And that's things like barium, boron, cesium, iron 3+, rubidium, strontium, so on, titanium. Clinopyroxene by far has the most complexity with 17 elements. There are several major elements in these phases: iron, magnesium, sodium, calcium, aluminum. Those are the predominant ones, but they only account for 63% of the variance in the data set, right? And the other 37% is accounted for with other elements. And these are things like manganese, chromium, titanium, and a lot more. Again, as complicated as this system is, we can still make predictions on all 17 of these elements, which is pretty exciting. So lastly, we have orthopyroxene with 11 chemical components. Within this system, the vast majority of the components are iron, magnesium, and manganese. In fact, they account for 98% of the variance in the PCA space. Orthopyroxene has significantly more limited chemical space when compared to clinopyroxene, but we can still predict these small amounts of other minor elements like cobalt, chromium, and titanium. So we're able to characterize a huge swath of chemical space in these 4 mineral systems. And in fact, we're covering all of chemical space that these minerals are known to form in. So that's all we've seen in nature, right? And that's quite a feat. And we're very excited to be submitting the first paper on LDL and minerals probably next week. I have a couple little edits I need to make probably tonight after this meeting. And this method is immediately applicable to obviously the minerals observed in Gale Crater, and that was our main driver. It'll give us a much better picture of the geologic history of the Martian surface. And while it will not replace high precision chemical analyses on Earth, it can allow for quick assessment of major and minor chemistry in laboratory or field settings. And most importantly, really, looking ahead, this method could be very useful for future planetary missions in which similar X-ray diffraction technology is employed. Being able to send an instrument capable of determining the structure and composition of minerals to another planet will give us a level of understanding of its geologic history that is beyond what any other type of instrument can do. And we did that with machine learning, which is pretty cool. Okay, so the other area of study I'd like to mention is mineral network analysis. We got into this because minerals are so information rich and so complex and so diverse that we needed a better way to visualize these systems. Like I said, I've only shown you just little bits and pieces of the types of information we can get in minerals. And I'm sure you already have a picture just of how complicated it is. And network analysis allows us to incorporate and display many dimensions and attributes at once. So it's offering the opportunity to explore visually and analytically these very complex systems and recognize trends that were previously obscured. Let me explain a little bit about how networks work. Networks are made up of nodes and links. Each node represents an entity in the data set. In our case, each node will represent either a mineral species or a mode of formation. The links represent relationships between those nodes. So in the case of our networks, it signifies that a specific formational environment is known to produce a specific mineral. These links and nodes come together to form an interconnected network, which could represent all of the minerals in a specific deposit, an entire planet, or in our case, all of known mineralogy. Note that if a network has one type of node, like say only minerals, it's called unipartite. But if we add another type of node, like say paragenetic mode, we call that a bipartite network. And I'll show you both types of networks in a moment. Another important point about visualizing these networks is that you can adjust the color, size, shape, transparency, weight, so many other factors of the nodes and links in order to represent whatever attribute of the data you want. Generally, you can represent up to 8 variables at once over any number of dimensional space. So networks are not just visual tools, of course. There are also many different metrics and machine learning methods you can run on the network or on the network data object. Just to give you an idea here, here are some of the most basic local network metrics that we can run for any node. These are metrics like degree, which tell us the number of links connected to a given node. Betweenness, which determines the number of shortest paths that pass through a node, which essentially tells us if a node is a broker node between two disparate groups or two disconnected communities. And lastly, I'll mention eigenvector centrality because I'm going to show it to you later. And it's essentially a recursive metric for determining the importance of a given node relative to the importance of other nodes in the network. These are all metrics that tell us about individual nodes within a network, but there are also global metrics that can tell us about the network as a whole. And there are other methods like community detection that can also tell us about groupings and distinct communities within the network. So analytically, there is a ton to do. I'm mostly going to talk visually. We'll talk a little bit about metrics as well. Okay, so let's have a look at some of these networks. Without going into great detail here, some of the discoveries that we've been able to make include that there are embedded trend lines within these data sets and within these networks. These include age, chemistry, oxygen fugacity, sulfur fugacity, so on, lots of things. The power here is that all of these trends were recognized visually within these networks. We create the network and boom, this information is just popping out of there. So recognizing and then quantifying these trend lines allows us to do things like obviously recognize phenomena like geologic processes and relationships. And it also allows us to do things like predict missing values within our data. Often in sample-based data, it's small, it's sparse, it's heterogeneous, and being able to predict missing values actually is really important. So from a data processing standpoint, it's pretty cool. We can also recognize and characterize punctuation events in the geologic record. This includes things like mass extinction events in the fossil record and major shifts in the environment or in the conditions of a mineralizing environment. And actually, I think we have time for a quick non-mineralogical aside, because I think it's really cool, into discovering the signature of mass extinction or punctuation events. The network we're seeing here is that of the coexistence of animal families through time, starting in the Cambrian, going into the Paleozoic, and then into modern fauna. So each node represents an animal family, and two nodes are connected if they have been found to co-occur in the same rock unit, or in other words, if they live together and, well, died together at the same time. There's an obvious timeline, which we expect, given that we're dealing with Darwinian evolution, although it's interesting, we see this in mineral networks too, which is evolution, but not Darwinian. We expected to see the timeline, but we didn't expect to see these pinch points in the network. And it turns out that each of these pinch points correspond to a known mass extinction event in the fossil record, which makes sense when you think about it. But it's very important when trying out new techniques that you learn to identify things you already know to be true, like these mass extinction events. Now we know that when we see these pinch points in a network, it may signal a punctuated event in the evolutionary record. So when my paleobiologist colleagues created a network of trilobite taxa connected based on co-occurrence again, they noticed one of these pinch points in the network. And this pinch point didn't correspond to any well-known mass extinction event. So my colleague Drew Macenti started digging into this problem and found that, sure enough, this punctuation event corresponds to a massive faunal turnover towards the end of the trilobite record. A few older papers had kind of speculated that they thought maybe something had happened here, but no one had really been able to characterize it. And with one glance of this network, we were able to clearly see this event, and my colleague was able to characterize it. So very powerful and a visual tool. So coming back to the mineralogical examples, we can do comparative planetology and characterize the unique signatures of planets and planetary environments. What you're looking at here is a network representation of Martian meteorites and their minerals. And very excitingly, in my mind, we can also characterize planetary scale biosignatures and the diversity and distribution of mineral species across the planet. And I'll talk in more detail about how we're approaching that from some of these types of questions in a few minutes. And before we get into that, I'd like to step a little bit more deeply into a project that employs network analysis among other advanced analytic techniques. And I really feel that all of these other projects we've been doing over these past few years have led us to this point, which is the evolutionary system of mineralogy. So I'm working on this with my colleague Bob Hazen, who I mentioned earlier. And like I've said several times today, minerals are incredibly information rich. This new system of mineralogy integrates their diverse characteristics and properties. These are things like trace and minor elements, isotopic ratios, structural defects, textures, morphologies, all of the other variables I've shown you up until this point. And it gives us the opportunity to gain a multidimensional holistic perspective, the dynamic chemical, physical, biological, and planetary materials and processes that have occurred through deep time. So you can understand why it's all coming together, right? We're bringing together all the things we've been thinking about, all the things we've been doing to make this one evolutionary system. Now, there's a lot going on in this system, and I'm not going to go into all of those details. There's this long series of papers. I'd be happy to send them to you or chat about it if you're interested. But there are two components of the evolutionary system of mineralogy that I'd like to introduce to you today. The first component of this work asks the question, what are the modes of mineralization across our solar system and through deep time? So what are all of the ways minerals can form from the dawn of our solar system through today, from Earth to every other body we have chemical knowledge of? And as if that question alone isn't big enough, what are their relationships to the geologic, geochemical, and biological processes that form them? So, just tiny little questions, no big deal, should be easy. This work began by surveying the scientific literature to extract every single mode of formation of the nearly 6,000 known mineral species. Through this survey, we were able to identify 57 different paragenic modes or modes of formation or modes of mineralization. And we arranged them more or less chronologically in terms of planetary or mineral evolution. This resulted in nearly 11,000 6,000 combinations of mineral and mode of formation. So as you might imagine, this is a huge data file. I'm just showing a fraction of it here. If you're interested in seeing these data in their entirety or in using them for your own work, feel free to reach out to me. They're also open and available through our paper in American Mineralogist, or you can search these paragenetic mode tags on the IMA site that I mentioned earlier. Okay, so we have all of these data, and you've seen a little bit of what they look like in a spreadsheet, but you can't tell anything from that, right? I mean, it's hard to gain information from that. So how do we visualize this as a whole system in a way that we can actually extract meaning from it and explore the relationships between minerals and mineralizing environments? I think you know where I'm going with this, and it's networks. Here is the network of the data object I just described to you. So what you're seeing here is a graphical representation of the relationship between all known mineral species and their modes of formation on Earth and other bodies in our solar system. The brown nodes represent the 5,600 mineral species. The colored nodes represent the 57 paragenetic modes or mineralizing environments. And we've grouped them into 11 categories and colored them accordingly. So these groups are more or less chronological, and they're listed in the legend on the left. And they're things like high temperature alteration, early biosphere mineralization. So just to remind you, if a brown mineral node is linked to one of the colored environment or paragenetic mode nodes, that means that that mineral is known to form in that environment. And there are several recognizable features in the topology of this network rendering, but I'd like to point out just a few to give you some familiarity with how we look at these graphs. So the first is that if a mineral forms in only one mode, you'll see it dangling off the network like the mineral nodes highlighted here. If the mineral forms in more than one way, it would be pulled in more towards the center of the network. The topology of these unique mineral nodes can also tell you something about the uniqueness of the associated mineralizing environment. For instance, when you see a large group of these one mode minerals together, you know that there is something particular about that paragenetic mode that results in a suite of unique minerals. If we take a look at some of those modes of formation more closely, we can start with high temperature alteration environments. You can see that these environments produce a lot of mineral species, a high proportion of which are unique to those environments, particularly those in the case of hydrothermal deposits and certain types of metamorphic deposits. Whereas contact metamorphism of carbon, phosphorus, iron minerals tend to have a slightly higher proportion of minerals that can form in other ways, and that's why it's being pulled in a little more towards the center of that network. Another set of really interesting systems is highly evolved igneous systems like agapaitic rocks and granite pegmatites. They tend to have a large number of unique mineral species as well as a high mineral diversity in general. In this case, that is because these modes of formation are very good at concentrating rare elements, and rare elements form rare minerals. So we end up with a suite of many, many minerals that are unique only to those specific environments. And that's very clearly demonstrated in this network layout. You can immediately recognize them. So in contrast, the closer a node is pulled in towards the center of the graph, the more interconnected it is to the network and the system itself. In other words, if a mineral is pulled in towards the center, it means it forms in several different ways. And if a paragenetic mode is pulled in towards the center, it means that it produces minerals that are also formed in several other ways. So let's take a look at some of those environments and that have this more centralized trend. So first, let's take a look at primary mineralizing environments that popped up in the Hadean, things like mafic and ultramafic systems. These mineralizing systems produce some unique mineral species, but approximately half also formed through other means, thereby pulling them in towards the center of the graph. The mineralizing environments that popped up in the Hadean hydrosphere in large part are even more centralized in the network. There are a couple of exceptions, but others like serpentinizing systems, hot springs, low temperature alteration, and so on, they form minerals that also form in one or more other environments and are therefore highly centralized. Similarly, minerals associated with plate tectonics often form in other modes as well and are pulled in towards that center. So you probably already observed quite a few trends that I didn't even mention, but I'd like to summarize just a few key takeaways for you, specifically as they pertain to water, paragenetic diversity, rare elements, and biology. So first, we examine water's role in mineralization with each of the paragenetic modes associated with water and hydrous processes highlighted in the graph. You can clearly see that water plays a huge role, with 80% of known mineral species forming through processes that were driven or influenced by water. Now, for the diversity of paragenetic modes, most mineral species have only one or two modes of formation, with 59% of minerals having only one paragenetic mode, which you can see here displayed on this graph, and 24% having exactly two modes of formation, which mean that 83% of minerals have form in only one or two ways. There are notable exceptions, such as pyrite, which has the most paragenetic modes of any mineral species at 21. You can clearly see its incredible diversity of formational environments and its spread all over the network. We also noted the role of rare elements in mineral diversity. 40% of minerals require one or more rare elements, and these 42 elements, which are things like rare earth elements, platinum group elements, arsenic, molybdenum, so on, make up fewer than 1 in 10,000 crustal atoms. So it's pretty astonishing when you think about their contribution to mineral diversity. Many of the rare elements make up rare minerals, which are these phases we're seeing uniquely associated with just one formational environment. There's so many things we could continue to explore here, but let's turn our attention to life. Firstly, 50% of all known mineral species can form through paragenetic modes that are influenced by life, while 34% of all known mineral species form exclusively through biotically driven processes. Some of these paragenetic modes are direct biomediation, like microbial precipitation in guano minerals. Others are associated with biologically driven or influenced processes, for example, the oxidation of our atmosphere by cyanobacteria during the Great Oxidation Event. Looking at this network, you can immediately see that the biological minerals are heavily grouped towards the upper left corner. And this is interesting because while there are many minerals that form through only one mode of formation, well, not many actually, only a handful in this case, but because the vast majority of them form in two or more ways. Okay, so unlike the other paragenetic modes throughout the network, however, this doesn't cause the highly connected nodes to be pulled into the center. That's because these minerals tend to form in other biorelated modes, thus creating this sort of subgraph that is unique and distinct from the rest of the network. Of course, the big question is why? Is biologically driven mineralization fundamentally different from that of purely geologic processes? Are bio-driven minerals fundamentally unique? And is the observed network topology or subgraph a signature of life on Earth? I think the answer to all of those questions is yes, but there is a lot of work that needs to be done to evaluate that. Because we can clearly see that these minerals and their modes of formation are behaving differently than the rest of the network. So our first step in evaluating why that might be is to analyze the network metrics. So let's do that by looking at this system in a slightly different way. First, I'm simplifying this network by transforming it into a unipartite network with the nodes representing mineral species, and they are colored by whether they form in only abiotic modes, shown in blue, only in biotic, shown in green, or if they can form in both, which is shown in red. And a link between two minerals means that they share at least one paragenetic mode. You'll immediately notice that there's this seemingly bioticness trend line going through the graph, with minerals being largely abiotic on the right, moving into biotic and abiotic in the center, and then purely biotic on the left. From here, I want to evaluate both global and local metrics. There are trends in several of these metrics, but the one that shows the most pronounced characterization of the biotic trend is eigenvector centrality. Here you can see the nodes are now sized according to eigenvector centrality, which again is a recursive metric that demonstrates the relative importance or influence of a node on the overall topology or structure of the graph. I'm sure you're noticing exactly what I noticed. The biotic minerals have much higher eigenvector centralities than abiotic minerals, despite there being other highly connected, even more centralized nodes in the network. The bio-influenced minerals dominate eigenvector centrality and are therefore the most important and influential nodes in the graph. So this leads me to ask, is this a clear signature of biological activity on our planet's mineralogy? And can we expect to see similar patterns of mineralization and mineral relationships on other geologically active rocky bodies? I think the answer is likely yes, with a lot of caveats for the second question. And of course, there's a lot to unpack and explore here, and I'd love feedback from anyone on these ideas and how we might critically test and expand them. We're beginning to evaluate them by exploring several questions, which include, is biotic mineralization more continuous and therefore more opportunistic or flexible than abiotic systems? Probably. Does this trend hold true when mineral abundance or frequency of occurrence is introduced? It's going to make a big difference. Is atmospheric composition influencing the connectivity of biotic minerals? Most likely. And how does modern Earth's topology compare to that of chondrites, the Hadean Earth, or Earth evolved to the point of plate tectonics? We've actually made these networks and we're in the process of evaluating them. And I'll tell you, they are very, very different. And so I think there's really something here. And in summary, biology has impacted Earth's mineralogy. And this impact is observable and quantifiable within Earth's mineral networks. And therefore, I hypothesize that what we're seeing here is a mineralogical sign of life. So I've shown you a brief example of how we can visually and lightly analytically explore these networks. And you may have an idea of some of the ways in which we can use metrics to quantify the trends that exist within a network. And we've seen how we're characterizing observed trends related to various geologic and biologic phenomenon. But what about situations where I don't know anything about the origin of a mineral specimen? What about rover missions and sample return missions from other planets? Or when you're in an uncharacterized environment in the field, can we predict the formational environment of a mineral specimen of unknown origin? So the answer is yes, in many cases. And this is the last project I'd like to mention. I'll go through very briefly. And that is another component of the evolutionary system of mineralogy, and we call this natural kind clustering. So let's take, for example, pyrite. Pyrite forms in many different environments and many different ways, some of which have biological input and some of which don't. But if I tell you that I found pyrite on Mars, what does that tell you about the Martian environment that formed it? Not a whole lot. Remember that I told you it can form in 21 different ways. So it tells you that I could have had a range of conditions and materials, but it's not very helpful for determining the geologic conditions or if there was biological input into those environments. However, that information is locked within each mineral specimen. In order to extract that information, we've turned to a massive data set, nearly 6,000 samples of pyrite. So here we are looking at major, minor elements, some textural information, isotopic ratios, and we can use machine learning, specifically cluster analysis, to examine the multivariate correlations across the various major, minor, and trace elements within these samples. So here you can see the preliminary cluster analysis shown as a PCA plot. We've been able to determine that there are some clear delineations associated with pyrite formational environments. One of these very clear delineations is associated with temperature. Samples cluster into two distinct groups, high and low temperature formation. These groups can be further clustered by their specific formational environments within high temperature and low temperature regimes. Then with this classification algorithm, I can take any pyrite specimen of unknown origin and I can determine how it was formed. And potentially in the future, we'll be able to say whether there was biogenic input to that formation. So I can pick up a piece of pyrite on Mars and I can tell you if life played a role in its formation. And I think that's pretty exciting. We can apply a similar clustering classification to many other mineral systems, and I've listed a few of them there, a lot of them. So I've gone over a number of projects, so I'm just going to summarize some of those key findings just to bring them fresh to your mind for maybe questions you have. We've observed and quantified that a planet's evolution is recorded in its mineralogy. We've been able to predict the number of missing mineral species on Earth, and with the same work, we've hypothesized that Earth's mineral diversity and distribution is a planetary scale biosignature. We predicted the location of unknown minerals, including critical minerals related to green technology, analog environments, and mineral inventories of selected locations. And we've estimated the complex major and minor element compositions of minerals on another planet based on X-ray diffraction data alone, and have thereby increased the value of sending an already very valuable XRD instrument on planetary missions. We've observed high-dimensional multivariate trends embedded in network topologies, and we can use these to address various scientific questions. We've characterized all mineralizing environments through space and time. And we've quantified the role of major drivers of mineralization, specifically the role of water, rare elements, and life, although there's a lot more to do there. And we have a particular emphasis on quantifying potential biological signatures in Earth's mineral networks. And we are using cluster analysis to classify and predict formational conditions of mineral specimens based on geochemical data alone. And through this work, we're developing an evolutionary system of mineralogy that places mineral classification in the context of planetary evolution. So in conclusion, Mineralogical frameworks coupled with advanced analytics and visualization techniques offer a view into Earth, planetary, and geobiological systems that is unprecedented. This multidisciplinary and multidimensional approach will reveal mysteries about our universe that we have never seen before. So I'd just like to reiterate that the future of mineralogical science, and really Earth and planetary science as a whole, is data-driven, interdisciplinary, and multidimensional. There's a whole lot left to explore here. So please feel free to reach out if you have questions, and we should have time for some questions after this too. But if you have ideas or you'd like to collaborate, and speaking of which, I'd like to just briefly mention that I am transitioning to Rutgers in the fall, and I'm hiring for several roles, including a research professor and students. So if you know of anyone who may be interested in working on these types of questions, please send them my way. And with that, I'd like to thank my many collaborators and funders for enabling me to pursue my ideas, however out there they may be. And I'd like to thank the hosts of this great event. And most of all, I'd like to thank you all for tuning in to learn about my work. So thank you, and I hope we have time for some questions.
Thank you very much, Shaunna. What a great work that you're doing. And totally enjoyed all those graphics and stuff, as well as the data. Thank you very much. So let me let everybody know that the floor is open for questions. While people are sending in their questions, let's start. There are a couple of questions of the one of the very first few slides on the mineral evolution you had. And first of all, there is a question about those data, that the numbers were very precise. So were they actual counts or were they predicted data?
Was this for, let me go back to those slides. Was this for
the mineral evolution slide?
Ecology work, maybe, where we were predicting the number of missing species?
But the one before that, when you mentioned that in each stage of the
in the stages.
planet's
Okay, yes, absolutely.
evolution, we have a certain number of.
See if it'll show. Oh yeah. So basically, this we have quantified through actually that later work that I brought up, where we were going through and characterizing all of these mineralizing environments. So this should be thought of as a lower limit, right? This is what we know based on what has been observed and what has been predicted in some cases. Some of these are hypothesized to exist and have not actually been observed, but reasonably they should be. So each one of these numbers is assigned to a paper in which a scientist found this, or very reasonably said we should find this. So that's why they're very precise numbers. That's a great question. Yeah, well, how can you be so precise? Well, because we went through all of the literature, and I really have to thank my colleague Bob Hazen. This was one of his COVID projects, maybe obsessions, right? So he went through all of this literature. I think it was about 6 months that he spent almost all of his time going through the literature. So those numbers represent a very exhaustive literature review. And again, they should be treated as a lower limit. Those are the things that we know to occur, and there may be some things that we haven't observed yet that we will, and these numbers will keep going up.
Excellent. And now, based on this information from the papers and the numbers you set for Mars and Earth, if I recall correctly, Earth's is almost twice. Does that not pretty much eliminate the chances of biology on Mars?
Yeah. So I always try to be really, I'm like, oh, when I present this, right? Because that is a conclusion that is very easily drawn from this, right? I think that we really want to think about, if life existed on Mars, what would it have been like? And I think that it really we would have been dealing with an anoxic biosphere. We would have been dealing with a subsurface biosphere. Actually, one of the questions that I've been really interested in, and I didn't have time to go into today, in part because I have no idea how to answer this and I have no data or anything to back it up, but I want to know, okay, we're characterizing what life looks like on Earth. How has life impacted the solid Earth, right? But what would it look like on Earth or Mars if life didn't stick around so long, right? We've had billions and billions of years of life on our planet. Well, a lot of the geologic activity, which you need in order to keep a biosphere going, stopped, like 3 billion years ago on Mars. So if it did have a biosphere, it was short-lived. It was probably more limited in both in potentially geographic extent. It was more limited in genetic extent, in the types of environments that it occupied. So, I used to think actually that, well, yeah, the mineral diversity that we're seeing on Mars, so it's about 1,100 and we have 6,000 minerals on Earth. Okay. And half, at least half of those minerals can form through biomediated means, 34% of which only form through biomediated means, right? So a huge chunk of that is life on Earth. And so, we only have this very small number of minerals on Mars. And I used to think, well, that doesn't bode well for the search of life on Mars. But I actually don't think that that's true, because I think we're dealing with two very different systems from the biological standpoint, right? We were really, really similar up until a point, and then we deviated significantly. And so I think we can learn a lot about what life does on this planet, and it can help us recognize some of these overall statistical patterns and trends that we may be able to translate to Mars. But I don't think that what we've observed so far necessarily precludes life on Mars. And another thing to keep in mind is that we got a lot of Mars to explore, right? So we've done remote sensing, but it's not very fine scale. We've done some rover missions, but not that many. We've never done a sample return. The only pieces of Mars we have are meteorites, and they are just igneous rocks that are, pretty basic. That's not true of Black Beauty. Black Beauty isn't more interesting, but they're pretty limited in what they're telling us about Mars. They can tell us a lot, but they're still limited. It's a big planet. So I think that we really need to do a lot more work before we can say that. Personally, I think there probably was an anoxic biosphere on Mars, but I don't have a lot of information to back that up. But I used to think that that probably wasn't true. And my opinion actually has changed on that. So I do think that there was life on Mars. It probably mostly there could still be some in the subsurface, I don't know.
Great, thank you. So now let's turn our attention to the in-person audience. Barbara, do we have any questions?
The question that was asked is regarding the projected missing minerals, and the question basically it's do we think, or do you think that those were all generated in one period of time, or were they generated sort of all through the history? Is that basically it? You were more elegant in the way you phrased it. Okay.
That's a really interesting question. And I don't know if I've really thought about that. So I think that we probably could characterize more specifically where we think in this stages of evolution these missing minerals were likely to have formed. But I've not really characterized that. That's a cool question, actually. I don't know. I don't know the answer to that question. So what we have done is we've looked at things like things that affect how likely a mineral is to be detected. So things like we know if something doesn't form big, pretty crystals, it's less likely to be detected, right? We know if something is white and kind of crummy, like a lot of sodium minerals, we know that they're less likely to be detected. If they look like other common things, they're less likely to be detected. If they are not of economic significance, they're less likely to be detected. So I think you absolutely could start tying in some of these pieces to be able to say, okay, what are the periods in which we are missing the most minerals? Now, we are definitely missing minerals that were more ephemeral throughout the various stages of mineral evolution. Things that when it rains, they go away. We're definitely missing those. We know we're missing those. So we're missing a higher proportion for that reason, and just for loss due to plate tectonics and crustal recycling. Things that are older, we know that we just have less of that mineralogical record. And so there is some sampling. There's a preservation bias there in addition to a sampling bias. But yeah, so I think we could do that. There's also a technological bias here. So that's an interesting study that my colleague Ed Grew was looking at, where he looked at these accumulation curves based on technological advances. So if we only have X-ray diffraction, these are only the minerals that we could discover. And this is the accumulation curve and how many minerals we would have said existed. And okay, well, now we have microprobe. So now we can do chemistry beyond blowpipe chemistry and things like that. We can do fine grain chemistry. Now here's the accumulation curve. Now here's how many minerals we can discover. And then, the advent of finer scale technology and things like that, and synchrotron and so on. So we've looked at this in a lot of different ways, but I don't think we've looked at it in the way that you suggested, which I think is a really cool idea.
Great, thank you. Now, as a follow-up, can you also mention a little bit about the aging techniques that you use? Is radioactivity the method you determine the age of a mineral that you find, or what other methods do you use?
We use everything, actually. So we will, and actually, if you go to the mineral evolution database and you pull up, say, a mineral that you're interested in, and you get all of the ages, you'll notice that the ages are color coded. If you scroll all the way down to the bottom of the page, you will see that there is the color scheme there, and they're colored by the way in which they were dated. So sometimes it could be, radiogenic techniques where you have directly dated the mineral. Sometimes it could be that you have dated another mineral in that deposit that is a single mineralization event. Sometimes it's stratigraphic dating, right? And so our bounds will be a little bit bigger. So we know it's younger than this and older than that, and we have larger bounds. And so we get, it's almost like a confidence level, actually, as you go down. So it's directly dated. We're very confident in that. It's, the mineralization event is dated. We're pretty confident in that. And then it becomes more and more ambiguous as you go down the list. So we, in our data collection, we would take anything that was, scientifically feasible, right? All of this came from peer-reviewed scientific literature. So any technique that is sound, we accepted.
Thank you. And while we are on the practical questions, you mentioned the Citizen Science Carbon Mineral Challenge. So how are these conducted? Do I go to my backyard and take a soil and rock sample, send it to a laboratory, or how does it work?
You could, if you think that there is something new back there. So most of what was happening there, so there was the mineral collection community. I don't know if you're familiar with this group, is incredible. I mean, these people, they call themselves like amateur mineralogists or mineral collectors, but they have, much like I think most of the members of your club have knowledge about astronomy, they may call themselves amateur astronomers, but the fact is they probably have knowledge that is rivaling that of a professional, right? And we find this to very much so to be true of the mineral collecting community. They're absolutely incredible. And so they actually have a lot of knowledge about where it is likely to find some of these minerals. And so, for instance, if we're saying, like the sodium minerals I mentioned earlier, right? That are just these crummy little white things that no one cares about. We put out the call like, hey, you probably need to go in museum drawers and look at other things where it's been characterized as this one sodium mineral, and it's probably actually several, right? And you need to go and actually look at this. So in some cases it was like that. We're looking at the carbon minerals. It's like, okay, well, where are you finding unique carbon minerals? If you remember when I was showing those networks earlier, environments that produce unique minerals, right? And so they already have this large mineral diversity. They already have this concentration of rare elements. The likelihood that you're going to find something else there is much higher than if you go to a location that's just like your standard granite, you know? And so there are certain places that you can kind of look to have a better idea that, okay, likely this is something. And a lot of the collectors, they have microscopes, and sometimes they have analytical equipment where they can actually have a pretty decent idea that they have something new before they even send it to a lab to do those analyses. So it's the collector community is pretty incredible.
Yeah, it's a tough competition then. Okay.
Well, there's a lot of minerals out there.
Thank you. Barbara, any in-audience questions?
Any other, yes, sir? Oh.
About minerals in the asteroid. There are thoughts about trying to do more analysis of what asteroids might be composed of, and kind of a speaker thinking about that, or is that other people that have?
Okay, we have two questions coming in. The first one is regarding minerals and asteroids. And the question is, what kinds of minerals, and are those part of the work that you are doing? If not you, who might be looking at that?
Yeah, absolutely. So if we go back to this diagram here, so you can see that, asteroids, you're kind of getting into this range where you're getting this starting to have some planetesimal differentiation and alteration. So we actually have papers in which we characterize what you would expect to find in most asteroids. They're relatively primitive compared to Earth. And I mean primitive in a geologic sense. They've not had a lot of igneous evolution. So you're not going to have high concentrations of, say, rare earth elements and things like that. Probably not going to have high concentration of gold and things like that require a lot of geologic cycling to concentrate. You're going to have a lot of iron, a lot of magnesium, a lot of silicates, and some of these kind of very basic minerals, like what you pick up when you pick up a chunk of basalt. That's kind of like what it's going to be like. I think some of them can tend to be a little bit more metal rich. But yeah, I think that's pretty close. And so, yeah, we have papers where we kind of go through that a little bit, but we're kind of at this stage of mineral evolution here.
And you said there's a second question, Barbara?
Yeah, the second question?
Oh.
Impact of biology on mineral level. What about mineral impacts on biology?
Okay, the question is, you talked about the impact of biological processes on minerals. What about the reverse, the effect of mineral evolution on biology?
That's
Is that
such a
something
great
that's looked
question.
at?
Yes, that's such a great question. And when we're thinking about this, we really try to think about it. I'm a mineralogist. Ultimately, I want to know what it did to the crystalline surface of our planet. But we often try to think about them in terms of the feedback system, right? There's this loop, there's this relationship. And so I work with microbial ecologists, I work with biologists, microbiologists, geobiochemists who think about these systems first order. And we try to come together First of all, we have to learn how to speak the same language. And I will be honest, that is a feat. Like that takes a long time. Most of these collaborators I have had for 6, 8 years, and we now really can communicate. But it took a couple of years, I think, before we can still talk past each other. But I was actually just visiting my colleague Donato Giovanelli he's at the University of Naples in Italy for a week. We were there working on some of our shared projects. He's a microbial ecologist. And so his questions are always, okay, how is this geochemical environment influencing what life can do? And it is significant. It is the single biggest driver of what happens in a microbial system is the geochemistry that it is able to access. And so we think a lot about metal availability through time, and when were certain metals available in a widespread enough way for life to take advantage of that. And you can actually start to pin, they often know this microbe evolved after this microbe, but they don't have actual dates on that. Well, we have dates on rocks, right? We're able to do that. And so what we could do is actually start pinning, okay, this is when this organism started to come on the scene. And we know that because it didn't have an active source of copper, for instance, prior to that time, right? And so we think a lot about the ways in which it affects. And what we're doing now, that's really complicated and difficult, is trying to look at not just how does copper affect this whole microbial population? How does iron affect it? We're trying to say, how does iron, copper, magnesium, manganese, all of these things together affect this very complicated population? So mathematically, just from a numbers standpoint, it's really hard to answer these questions. But we love these questions. And so we keep scratching at them. But what we have found essentially is that geochemistry, probably mineralogy, rock type, geologic setting controls biology wholesale, full stop. And so we have several papers coming out. A few have already come out kind of looking at this, and we have several more papers coming out in the future that really drive this point home. I think it makes sense when you think about it, right? Like they need the access to chemical elements to do what they do. But as much as it makes sense once you say it out loud, there's not really a lot of that in the scientific literature, and not a lot of people have really been looking into that. So we're really kind of starting from scratch, it really feels like we've been scratching our way through this. But I find those questions to be fascinating. And as someone who really ran away from biology, who really tried to avoid, I went into geology because I didn't want to do biology. Like biology is awful. It's so complicated. It's so messy. If there's a rule, it's broken in some way or the other, And so I don't want to do biology. I want to do only non-living things. And I found in my life and my career, the more I don't want to do something, the more it ends up being the thing that I do, like math and coding and things like that. So, I have to be careful what I try not to do, because that's the future for me. So great questions.
Great, thank you.
Yeah. I think we have another question here.
Sure.
Yes, sir. The question is, has any of the kind of work you're talking about been done on moon samples, and has that given any information regarding the origin of the moon, or the condition of the moon, really?
Yeah. So I've not thought about the moon a lot. I'm kind of just starting to begin doing some of that. So I have several data sets where I've collected, mineral information for the moon, geochemical information for the moon, and I'm just starting to make those comparisons. So I have made, in the same way that we have the network of Earth, I've also made the network of the moon. I wish I had those to pull up right now. I don't have easy access to them, but just starting to compare the ways in which they're similar and different to Earth. I've not really thought about it from the sense of the creation of the moon and how that is related to Earth and Theia and all of this. Other people do, though. I mean, people absolutely spend a lot of time thinking about this. I'm more so thinking about it from the standpoint of developing network kind of fingerprints of different types of planetary bodies, with the moon being one example. And I think as I get further into that, I will be able to potentially start thinking about some of these things in terms of its origin and its relationship, chemically, mineralogically, formationally to the Earth, and the original body that likely collided with us. And but yeah, I've not thought a lot about that yet. But I'm in a very basic characterization stage, I guess you could say. But it's really interesting. It's very cool. We're going to the moon. We're going to be bringing back moon samples. And so I think as a result, I want to start shifting my thinking a little bit more towards the moon. Great question.
Thank you very much. Now, the other question here we have is about the scale of the variety of minerals we see. So one of the works that you do is to predict where you could find a certain mineral. What spatial scales are we talking about? And, for example, the questioner mentions the Gale crater on Mars. When there is climate change, when there's maybe a meteorite heating, it changes the minerals around it. To what scale does that affect on how much space are we looking at to find these?
Oh my goodness. So that's such a great question. And it is a question that it doesn't have a good answer, sorry. Well, it has a complicated answer. So what we consider to be a locality varies a lot. And it really just depends on the geologic environment that we're talking about, right? So if it's an impact crater and you're saying my locality is an impact crater, then it's the size of an impact crater, which can be small or, massive. Or it could be my locality is a vein within that crater, right? And so now my locality is this big, right? And so it really just depends on your framework, right? And so it really is, I think you really should think about locality in terms of a framework for asking a question instead of like a spatial unit, if that makes sense. And that is incredibly hard to do from a data standpoint. So when we refer to localities, we are referring to localities as defined in MinDat, because that is reproducible and that is, testable, right? So we use MinDat localities, but within MinDat, there is a lot of variation. I mean, some localities are, many kilometers across, some are tiny, but they do have them as polygons. And this is information that is extractable. And I should have mentioned there's also a new initiative now to create an API on MinDat called Open MinDat, where you can code and extract almost anything that you want. So if you're interested in looking at these polygons and their sizes, it would be kind of interesting to do a survey of, what is the distribution of sizes of the different localities, and to relate that to the minerals or the elements that are present there, or, tectonic settings, something like that could be kind of an interesting data survey to look at. But yeah, the size varies a lot, and it is highly relevant to the question that you're asking. So that's why I say there's not a really satisfying answer to that. I would love to say it's 2 meters, right? But it's not a grid. It's geologic. And so it varies a lot. And it's a problematic thing because you want it to be on a grid, Yeah.
Thank you very much. Barbara, do you have questions?
Any other
from me personally?
questions on this side? Well, I don't see anybody with their hands up.
Okay, so there is this other question. Now, we have mentioned like the discovery of so many minerals. Now, are there any planet or foreign celestial object specific minerals, right? Are there things that we have on Earth we don't have on Mars, or vice versa, or Moon?
Yeah, absolutely. That's a really fun question. So there are, when you go to bodies that are very different from our own. So for instance, on Mars, you don't really expect to find things on Mars that you wouldn't find on Earth. We do expect to find things on Earth that you wouldn't find on Mars because, we have plate tectonics, we have a lot of geologic cycling, we have trees that have roots, things like that. But and you can kind of think of Mars and Earth as they were similar bodies on a similar path, and then one stopped, right? Mars stopped. And so anything we find on Mars, more or less, we expect to find on Earth. Venus is a little bit weird because it has a really weird atmosphere. So if there probably are some things on Venus that are really high pressure, are really associated with highly acidic atmospheres that you wouldn't find on Earth. But the body itself, it's a rocky body like our own. But when you start looking at water worlds or icy moons and things like that, you do get pretty different systems. And so there you do expect to find different minerals. Some examples are like organic co-crystals. So they're like amino acids that are crystallizing and forming these funky things. And I think they've been able to create those in the lab, and that's how they're aware of what it should be. But there are, some of these icy moons or water worlds are like erupting these crazy organic co-crystals and stuff like that. So absolutely, on bodies that are significantly different from our own, we expect to find different things. Yeah, absolutely.
Thank you. And then the next question involves asteroid mining. Recently, there's a lot of discussion about potential targets. So can you comment on that? Do you think it's feasible? Are there how likely are there that you will find asteroids rich with precious minerals that we could mine?
Yeah, that's a important question. And it also ties into another important thing that I'll mention. There, like I said, most asteroids are going to be relatively primitive. So if we're talking about, if you're looking for iron, that might be a good source of iron. If you need lithium, if you need rare earth elements, if you need plutonium, whatever, you're not going to find it in high abundances on these bodies. So, and this is not my area of expertise, and there are probably exceptions to what I'm saying. And you always hear something in the news about this thing has this much gold, or this thing has that much, it would solve the world's energy problems or whatever. So there probably are some kind of funky bodies out there. But in general, that is not the case, right? There are going to be things that are relatively abundant, or are things that are on Earth, I mean, or they're things that iron is heavy, iron is big. Just the act of harnessing and bringing this back to Earth is so incredibly energy intensive that it would not make economic sense. And right now, we are not in such short supply of any element that it makes economic sense to go and mine this. So I know some people are thinking about like helium-3 on the moon and stuff like that. And maybe that's a little different. That's very light. We're going to the moon anyway. So maybe that's not such a costly thing. But being able to harness an asteroid is energetically incredibly costly. And what this really ties into for me is, there are some billionaire tech people out there who like to, I'm not going to say names, who put out these ideas, right? And they're cool ideas, right? They're super cool ideas. They like to say things like, we're going to colonize Mars. Super cool idea. I love it. I love pursuing that. I love the science that goes into it from a geologic perspective, from a horticultural perspective, from developing rockets and technology. I love it. What I don't love, and so I'll get on my soapbox a little bit, if I may, is the idea that we are going to be able to go outside of Earth to either attain the resources that we need or to escape the situation that we have made. So we're never going to colonize Mars, right? Like the ability to create an atmosphere with the solar wind just whipping away every volatile that comes up is nearly impossible. I'm not saying it's completely impossible. Some technology could come along and we may be able to do that. But billions of us, how many people are on this planet now? I don't know, 7 billion, 8 billion. It's the number.
Eight, yeah, almost.
Yeah, 8 billion people are not going to Mars. At best, it would be a few thousand. So I think sometimes this is pitched as an idea of like, this is how we're going to save humanity. Well, we're not going to save humanity. We're going to save a few incredibly wealthy or incredibly fortunate people. And the rest of us are going to be left with the mess that we have made of our home, right? And so I think that we want to be really careful about, spending too much, pinning our hopes on, oh, we'll get this resource outside of our planet. Oh, we'll be able to get outside of our planet. So I'm always a little bit like careful with those questions because I think that they're such cool, like scientifically, they're so cool. And I'm like, oh yes, like I am all for it. I am there. But I think societally, we need to be a little bit careful about the ideas that we're giving like the general public about these things, if that makes sense.
Absolutely. Yeah. Thank you. Okay, Barbara, do you have any in-person questions?
We were just advised that a group needs to come in, so we're going to have to close down at the at Chapman.
Okay, so let me ask the last question, which I think it's going to be a good ending. Now, is the mineral evolution on Earth mostly over, or will there be another epoch of further evolution?
Human activity is causing, I've not really tried to quantify this, but my assumption would be if I did, is causing a more rapid mineral diversification or diversification of solid crystalline material. We don't always consider man-made crystalline material to be minerals. And there's a whole thing with the IMA that we won't get into. But if we actually took all crystalline solid phases, we are in the most major mineralization event that has ever taken place in Earth history right now. If you think about concrete, if you think about all of the material, like the cool technology stuff that we're making, all the different material science that they're making, like we're making all sorts of stuff. I mean, thousands and thousands and thousands and thousands and thousands of things that are like minerals. They're solid crystalline phases. And so it depends on, we argue about what is a mineral. It depends on what you call a mineral. I tend to think, when aliens come here in 3 billion years and they look at the strata that are associated with human activity, I don't think they're going to distinguish, oh, well, did a volcano make that or did a microbe make that? Those are minerals. But if a human made it, it's not minerals, right? No, they're not going to make that distinction. And what they're going to see is this incredible diversity of crystalline material. So right now, boom. Yes.
What a great note to end on. So again, Shaunna, thank you very much for a great talk. And I hope we could have you back in the future. And you also had other topics that you could have talked about, but this was great. Thank you very much. So I would like to also thank everybody for staying with us, and I apologize for the few people that I didn't get to ask their questions. With this, please do check our calendar on the website for all the future events, and hope to see you next month with another meeting. Thank you, everybody, and have a great night. Bye-bye.